Hi everyone, my name is Tom Carlitos. I'm the founder and the Project Steering Committee Chair of the pygeoapi project. Today I will walk you through the origins of pygeoapi and some history on where pygeoapi came from. I will give you an introduction of the project itself and what it is all about and what you can do with it as well. I will provide some insight into next steps as we move into the future. The first thing I wanted to cover with regards to this presentation is where sort of pygeoapi originated, and maybe give a bit of an overview on where the current API efforts are coming from. So pygeoapi is an OSGO project. It implements a number of different OGC APIs, which are application programming interfaces. And I'd like to give a bit of an overview on where that movement came from the greater community. So in the 1990s, we had a very strong concept of a service-oriented architecture, or an SOA. We had a lot of services based on XML and remote procedure over RPC, which is remote procedure protocol. A lot of SOA, and a strong concept of a relational database being the back end to a web service. So in the late 1990s, the Open Geospatial Consortium published the first version of the Web Map service. That was in 1999, and that was really the beginning of a number of different web services from the OGC, which helped us do visualization, discovery, and access of geospatial data on the internet. In the 2000s, we started to move forward with concepts such as Web 2 and Ajax, and getting a little bit more JavaScript involved. Google Maps in 2005 made their sort of slippy maps and tiles available through both Google Maps and they also had Google Earth for that matter. In the OGC, we continued with a number of additional specifications for not just maps or WMS, but WFS, which is Web Feature Service, WCS, which is Web Coverage Service, WPS, which is Web Processing Service, CSW, Catalog Service for the Web, for metadata. So over the 2000s, we started to see a lot of different specifications for the first generation of geospatial web services coming out of the OGC. And just like WMS, a lot of these were rooted in XML and the idea of the backend being a database. Some realities in associated with the first generation of geospatial web services. There was a strong focus on KVPs, or key value parameters, being part of the web service itself, and there was also a strong focus on using XML, or extensible markup language. We also saw the creation of GML during that time in the late 90s, which is a geography markup language. We also saw that first generation geospatial web services really treated HTTP response codes and the HTTP specification itself as a tunnel, and all of the first generation geospatial web services sort of overloaded how we currently use and are supposed to use HTTP. HTTP, Hypertext Transfer Protocol, has always provided us so many different ways and native approaches to how to provide error codes and how to provide error statuses, as well as payloads and so on and so forth. We dealt with those in a certain way in the first generation of geospatial web services, and that also resulted in very exhaustive specifications and requirements. So the first generation of web services, geospatial web services, we saw very large specifications, really focused on the 100% use case of trying to accomplish as much as we possibly can through a single specification, whether it was for vector data, raster data, processes, metadata, maps, what have you. And that resulted in very heavy specifications and very heavy implementations to be able to support those specifications. Here's an example of a first-generation geospatial web service using something called WFS, or Web Feature Service, providing a geography markup language document, which basically gives you, here we can see one feature member being returned from possibly a database of some vector data, providing the geometry and any associated properties. Some additional reality with regards to first-generation geospatial web services. Again, we needed, these implementations ended up needing complex machinery and architectures for services to be more approachable by the web, or search engine crawlers, or other structured data kind of systems. The other reality was these first-generation geospatial web services were also very difficult for web developers to implement, and it's been a challenge for mainstream web integration. So we had WMSs, WFSs, and all sorts of different other OGC specifications, and we found it challenging to make them available on a search engine to be able to find your data through a WFS on let's say a Google search or a Yahoo or a Bing search, or whatever your favorite search engine was. And that really painted a picture of the need to kind of evolve to maybe more modernized ways of providing geospatial web services, or APIs, in a way that was sort of lower barrier for web developers, and as well as the mass market or mainstream web integration. At this point, I'll walk you through some of the core canons of the current generation of I would say all web APIs, in addition to which sort of provided the baseline for geospatial web APIs in the current generation. So I'm going to talk a little bit about REST, JSON, OpenAPI, and Swagger. REST is representational state transfer. So this is an approach or a style which really makes the most use of the HTTP specification. So it really uses HTTP verbs, get, post, delete, to be able to interact with a given resource, whether it's geospatial or not. This applies to all sort of information architectures and APIs on the web, for that matter. REST also heavily focuses on proper use of HTTP codes, such as 200, which is okay, 201, which is the creation of a new resource on the web, 404, which is you look for a resource, you cannot find it, and so on. Heavy uses of URIs and content negotiation, so media types or MIME types, and the idea of having this stateless interaction so that anybody can sort of bookmark your web API call and visit it at any point in time later on. So this RESTful approach lends itself to mass market and search engine integration, as well as some performance enhancer with regards to caching as well. Along with REST, we've seen a heavy adoption of JavaScript object notation, or JSON. So JSON would be sort of a supersede, or would provide the same sort of capability or same purpose, at least over the web, for that XML did in the first generation geospatial web services. So JavaScript object notation is very easy to write, very easy to understand. It's very close. It's widely supported in programming languages, and it's very close to data types within programming language. So a JSON document is very close to a Python dictionary if you're a Python programmer, or it's close to JavaScript dictionaries or hashes, for that matter, or maps. JSON is also very popular among web developers, and it's, again, first class in RESTful web services. So the current generation of of APIs out there, where most of them are using JSON as the payload to return data or to return some other piece of information. There's no rigid standards on JSON other than the fact that JSON is a standard itself. But the good part is you can create dialects of JSON or different types of JSON to serve a specific information community. So GeoJSON is sort of JSON with some geographic rules to provide geospatial data through the JSON format. OpenAPI. So this is a very low barrier and quite powerful way to describe your web API in today's world. It describes a REST API. It describes all the paths or endpoints, and for each endpoint, you can describe what the request parameters are, what HTTP methods are supported by the endpoint, which is, let's say get, put, post, or delete, for that matter, as well as responses. What responses are supposed to look like. So you can even provide schemas for your responses in OpenAPI, as well as which HTTP codes a given endpoint would provide. And this really helps out a web developer or anybody wishing to use your web API further to be able to get a better idea through an OpenAPI document on a description of your API service. It's programming language agnostic, so you can provide OpenAPI typically in a machine-to-machine manner through JSON or YAML. This used to be sort of the Swagger. This used to be called Swagger before, but the actual specification graduated and became the specification that we know today as OpenAPI. Here's an example of a partial example of an OpenAPI document, and you can see this is JSON, although you can also provide it as YAML, and it gives some, in this case, high-level information about the API. But if we saw the entire document, you would see tons of information around all the different endpoints and request parameters that each endpoint in a given API provides. So again, a really deep description of the API using low barrier standards. I mentioned Swagger in the previous slide. So Swagger still exists, even though the API definition part of Swagger ended up becoming the OpenAPI specification. Swagger itself provides client tooling, and it's very web developer focused. It allows you to create web pages. And provide those web pages which give web developers an idea, a web developer friendly view of all the endpoints and all the parameters for the endpoints that are that you could use for a given web API. So just like we have an OpenAPI providing the machine approach of describing the web API. Swagger takes that OpenAPI machine readable JSON or YAML, and it renders it into a fancy HTML page, and it will give you, basically a nice UI experience to be able to test out a web API. So I've given up until this point, I've given some history on where we're coming from with regards to web services and APIs. I've also provided some overview on REST, JSON, OpenAPI, and Swagger. At this point, I will start to talk about more specifically what's been going on with some recent activity in the Open Geospatial Consortium with regards to web APIs. So the OGC stands for the Open Geospatial Consortium. It's a standards development, international standards development organization. There's over 500 members, and the focus is geographic information processing, whether it's standards for encodings or formats, or whether they're standards for interfaces. So specifically to the OGC API activity, there are a number of things that happened previous to the current efforts in OGC, which really laid the groundwork for the current efforts around OGC APIs. So in 2017, the World Wide Web Consortium published the Spatial Data on the Web Best Practices, which provided recommendations on formats, identifiers, access, licensing, provenance, and so on. And this really gave a springboard and a baseline of being webby and treating your geospatial data with a focus for web integration and exchange over the web. So you can see the URL to the best practice there. It leverages the W3C data on the web best practice, but it puts in addition, it puts a geospatial flavor on top of it. And this really laid the groundwork for us to be able to give more focus to geospatial data on the web and using these mass market low barrier approaches to facilitate mass market integration as well as search engine integration as well. Some of the design patterns behind the W3C spatial data on the web best practice and REST, JSON, Swagger, and OpenAPI for that matter. So again, being webby, developer friendly, very lightweight specifications compared to the past. So I mentioned the first generation of geospatial web services had really exhaustive specifications, which were trying to satisfy numerous use cases, which ended up being, I would say, very powerful specifications, but also very heavy to implement in their entirety. The current thinking around OGC APIs, which I'll get into a little bit later, takes on the approach of lightweight specification development, where we don't need the 100% use case or the 100% requirement. Maybe we need an 80% use case, which is good enough for most people, and then we can still develop the other more complex parts of the specification, but as extensions, as opposed to core requirements. The other big design pattern that I would say in current OGC APIs and web APIs in general is removing the use of HTTP as a tunnel. This means that we more properly use the native HTTP methods to be able to define our endpoints and URIs and URLs for that matter. So here you can see the URL that's striked out. That is a WFS1 or WFS2 Web Feature Service style request, and the second one is a OGC API or current web API approach or style of a request. So you can see we're not saying request equals get feature. We are saying HTTP get and then the URL below. And this is a closer use and a more native use of the HTTP specification, and it really rips out a lot of the complexity that's required to handle URLs like this. Whether you're a client to be able to generate those URLs, or whether you are a server, an API server, which means you have to handle these URLs to be able to do what the client is asking you to do. Again, modular specification development, core and extensions. We don't need 100%. And sometimes the 80% works just fine, and we're able to build things out in this manner. And the fact that we can do those in the specifications also lends itself to doing those in software as well. Timeline. So as I mentioned, the W3C spatial data on the web best practices was in 2017. And at the same time, there was the OGC API white paper. And this was really a valuable exercise in OGC to help provide some context and background on current state and where the OGC was with regards to geospatial web services, and it really provided a springboard to a clean break of defining new API standards, which again are a clean break, and they're built from scratch, as well as using the mass market low barrier approaches. And since 2018/2019, there have been a number of hackathons and code sprints that the OGC has coordinated and has run on behalf of the OGC API program, which I think has been very valuable for us to define these first generation geospatial web services as OGC APIs with a clean break using REST, JSON, OpenAPI, Swagger, and so on, to make new versions of WMS and new versions of WFS and so on using these new approaches. And here we are with regards to some examples of the OGC the current OGC API effort of standards. So you can see in brackets is the first generation standard that the API is designed to supersede or replace, for that matter, over time. So you can see most of the first generation OGC geospatial web services have been are being designed to be superseded or replaced by their OGC API equivalents, whether it's features, coverages, maps, tiles, processes, records, metadata, or styles, for that matter. A lot of them, they're all being designed to replace their predecessors. Now, having said that, we're also seeing new OGC APIs, which maybe were not as prevalent in the first generation. Around, for example, we have OGC API routes, as well as environmental data retrieval, and so on. A little bit more information on the current workings of OGC. So OGC activity is currently on GitHub, which is also lends itself to being webby, and the specification development itself is on GitHub. So you can go to github.com/opengeospatial, and you will see a number, all the OGC API specifications being developed right on GitHub. So you can see the issues that are being discussed, any discussions that are happening with regards to what needs to be supported, or if there's any things that need to be improved. And it really lends itself to a very collaborative approach to defining these specifications. So all that to say is the work being done to develop the standards is being done publicly on GitHub. The standards themselves are being written in ASCII doc, and they're now typically released as HTML, and they're very easy to work with, and very easy to put on the web and make them, again, more webby and web developer friendly. A number of the standards also have associated chat rooms or Gitter chats, or the OGC Discord channel, so you can interact with some of the specification, the leads of the specifications, as well as implementers of those specifications, whether it's clients, servers, parsers, serializers, and so on. This happens in the OGC Discord, in Gitter, as well as at these OGC API sprints that have been happening through the late 2010s. With that, I'm now going to walk into introducing pygeoapi, the project itself. So up until now, I've tried to provide a background of where things have led up to prior to pygeoapi being created in 2018. So pygeoapi is a GeoPython project. It's also an OSGeo project. So OSGeo is the Open Source Geospatial Foundation, and it is an approved project of OSGeo. It was created in 2018, and it's a Python project, and it belongs into the GeoPython suite of projects, which are all free and open source, and it's available on GitHub, for that matter. What does pygeoapi do? It's a geospatial data web API framework that is designed to support all of the OGC API standards, and which basically means it takes on the approaches put forth in the standards, implementing REST, JSON, OpenAPI, and Swagger for different geospatial data types and geospatial services. pygeoapi is OGC compliant already for OGC API features, as well as OGC API environmental data retrieval, and it is a reference implementation for both of those. There's an international team from many countries and many time zones, many experts that are working on this project, and it's really picked up a lot of steam since its inception in 2018. So the project really started out of a lot of work at these OGC hackathons or code sprints, and it has gathered quite a gathering of talented developers and core contributors. pygeoapi continues to strive to have a very simple baseline install, so you can get as complicated as you wish with the project, but in general, you're able to, if you want to stand up a minimal PygeoAPI implementation to test things out or to kick the tires, you can run these commands as you see on the screen. And if you go to the PygeoAPI website, or pygeoapi.io, you can see these exact steps. You can copy and paste them and run things. And in no time, you should have a PygeoAPI install up and running, and you'll be able to validate the install and interact with different data sets that are in the test install, the default install that is. For the most part, PygeoAPI leaves the data alone. It fits to the data, not the inverse. So that means that you put your data, you make your data available, whether it's through a relational database, a NoSQL database, whether it's through a file on disk, whether it's another API itself. PygeoAPI, for the most part, does not touch that data, does not change it or anything. It leaves it pristine and it leaves the data alone, and it just basically publishes the data through the relevant OGC API specifications. I will say the reason I say the leaves the data alone for the most part is because there's been some recent activity and recent updates to the PygeoAPI project around editing data or transactions, and I will get into that a little bit later. It also leverages the powerful ecosystem of Python packages. So PygeoAPI is written from scratch, but it reuses. It's also built by exception, which means it uses a lot of the Python packages that already exist, such as Xarray, such as Python requests, such as Shapely, GDAL, and so on and so on. It's not re-implementing what those very powerful libraries already do. It uses them and leverages them, which allows it to concentrate on what PygeoAPI is there for, which is the API capability, the web API capability. So in that sense, we do stand on the shoulders of giants with regards to upstream geospatial free and open source tooling that it's used in the project. It's a core abstract API, web framework agnostic. When I say web framework agnostic, that means by default we support the Flask web framework, which is in Python. All the web frameworks are in Python, but we also support Django or Starlet if you're looking for a synchronous API capability. It also is built off of a very simple configuration, a YAML configuration, and it supports automated OpenAPI document generation, as well as supporting a robust plugin framework. The robust plugin framework, I think, is something that is one of the core features of the project, where you're able to basically bind any data to PygeoAPI using this plugin framework. So if you're a Python programmer and you want to integrate your data into PygeoAPI, and there's no way to do it given the default plugins PygeoAPI supports, you can write your own. It also has very easy deployment and a wide deployment footprint or deployment style footprint. So you can install via pip, Docker, Conda, Ubuntu GIS, a number of different ways to install the project. I would also mention that we're also available on OSGeo Live, on the OSGeo Live project, to be able to run and test PygeoAPI from OSGeo Live itself. The default install has minimal dependencies, but as you start to add more data sets and more different style of data to PygeoAPI, you will need some additional dependencies to make sure that things are working correctly. But for example, if you wanted to serve out CSV data or GeoJSON data on disk, the dependencies are very minimal for you to stand up a very small footprint for that matter. Here's a component diagram of the actual of how PygeoAPI is designed. So you can see right in the middle of the diagram we have the core API, and that's a core Python API. The core Python API makes itself available through this web framework, which is basically what's providing the OGC API support. So the idea is the OGC API client who is connecting to PygeoAPI knows nothing about PygeoAPI, but they know about the OGC API itself that they're connecting to. So the web framework connects to the core API, which reads this YAML configuration, which you see on the right-hand side, as well as provides an open API representation, which you see on the left-hand side, which is the JSON or YAML description of the API interface itself. I mentioned the powerful plugin framework and the robust plugin framework that's implemented in pygeoapi. So you can see pygeoapi implements all of the data connections and all of the formatting and doing processes, for example, all through plugins. So everything is extensible from the plugin perspective. So we have a process plugin, which is basically writing your own web-based processes, or OGC API processes for that matter. We have plugins for formats to be able to build new return formats from the service, in addition to, let's say, JSON, which is the default. As well, we have these provider plugins, which is where a lot of the plugins we see are being developed. So that means integrating an existing data set or an existing API or some other service through this plugin mechanism to be able to make it available through pygeoapi proper. So extensible plugin type architecture that lends itself to flexibly allowing users and administrators to publish their geospatial data to OGC API compliant services. I'll walk you through some of the provider plugins that are currently available in the software. So we have feature data providers, which is basically publishing vector data through pygeoapi. And we have a number of different default feature data providers. So you can have your data, your vector data in Elasticsearch. You can have CSV files. You can have GeoJSON, as I mentioned before. A number of different SpatialLite, RDBMS, for example, a number of different feature data providers. I should also mention that we also have wide support for Postgres as well as a relational database model. In addition, for our feature data providers, we have a GDAL/OGR vector data provider, which is basically exposing all of GDAL's vector support, or the OGR vector support, through pygeoapi. And this basically unleashes over 100 vector formats, as well as it does paging reprojection, spatial attributes, and queries, and it also provides a facade which allows you to unlock existing WFS1 or WFS2 services. So basically, the GDAL/OGR plugin allows you to do whatever you do with GDAL, and whatever way you connect the data with GDAL or OGR for that matter, you can expose that through pygeoapi, which is really powerful because we're taking into account all the deep support that's available in this library, in this package for that matter, through the pygeoapi project. In this sense, pygeoapi starts to act like GDAL on the web, or GDAL/OGR on the web for that matter. Coverage data providers, so this is for raster data. We provide support for Xarray, so if you have multidimensional data, whether it's let's say a netcdf file, or whether it's a ZAR, a data store, you can provide Xarray support for that coverage data. We also provide coverage data plugins for Rasterio. So if you have GeoTIFF data, or if you have GRIB2 data for that matter, or anything else that Rasterio supports, then that can be made available through pygeoapi itself, as well as other formats. So this is our baseline sort of coverage data support. We also provide support for tiled data. So this is basically having vector tile data on disk and making it available through OGC API tiles for that matter. So you can have min.io, or you can have a directory tree of files on disk, and you can make that available through the tile data providers, which by default provides the Mapbox vector tile format. We also have plugins for map providers. So this is basically providing OGC API map support. We have recently implemented map server support, or map script support, within our map providers. I'll elaborate on that a little bit later, as well as a WMS facade. So this means if you would like to provide OGC API map support, our map provider plugins can help you out in this manner. If you would like to provide your maps through a different mechanism, obviously you can do that through the plugin capabilities. Again, these are the providers that are supported off the shelf, if you will, with the default pygeoapi install. We also have plugins or providers for metadata, geospatial metadata. You can have geospatial metadata in an Elasticsearch instance or a TinyDB instance, and this basically allows pygeoapi to expose this metadata through OGC API records, which will give you basically a metadata search capability. Our processing framework in pygeoapi. So pygeoapi supports the OGC API processes standard, and pygeoapi also supports it, obviously. And this basically allows, in a pygeoapi sense, to expose any Python workflow as an OGC API process. We support synchronous processes as well as asynchronous processes. For asynchronous processes, we have the concept of being able to implement a process manager for job control. So this means if you're doing an asynchronous job, an asynchronous request to pygeoapi to run a given process, then the process is logged within a job manager, and you can go back and check the status of that process, and then be able to get the result of that process once that the result of that job once it's completed. Our default processing framework is based on TinyDB, which is a file-based document store, but you can extend it to your own requirements, whether you have a Postgres database in the back or some other mechanism. You can implement your own pygeoapi plugin for any of the specifications that are supported. If you are a Python programmer, it's certainly viable to do so. pygeoapi, the pygeoapi plugin framework itself provides an abstract base class for a number of different plugins, and basically you would basically satisfy that abstract base class. Excuse me. pygeoapi also supports schema.org. So this is the idea of providing your data through supporting structured data searches. For example, here we see a view source of a given collection in pygeoapi, and you can see the HTML in the back in the source is structured in a way with schema.org, and this will really help with web-based discovery and structured data searches to be able to identify your data correctly and concisely through a search engine. And this has also worked with things like Google Dataset Search, for example. pygeoapi also lends itself and supports the linked data concept. So JSON LD is supported out of the box. There's some additional configuration that you would add to your given pygeoapi config or being able to expose a data set in a certain way that supports JSON LD. I'll walk you through some screenshots of core capabilities. So here's the landing page of a default pygeoapi instance. So here you can see everything about your pygeoapi install in a landing page. So you can see who the contact person is. You can see terms of service and license. There's links as well for collections, as well as spatial temporal assets, which I'll talk to a little bit later, as well as any processes which may be configured in the service, as well as the API definitions, or the Open API and Swagger definitions. For example, here's a view of the default Open API page in pygeoapi, which allows you again to find out the different paths and endpoints of a pygeoapi install and be able to interact with them through this web-based approach. Here's an example of OGC API features in pygeoapi. So here's an example using some lakes. That's basically a GeoJSON file on disk, and here we can see that through OGC API features, I can browse my lakes and look at a specific lake if I wish, and be able to get more information about that. In this case, that polygon feature. So OGC API features is the standard that's designed to supersede WFS 1 and 2 for that matter. pygeoapi also supports OGC API coverages. So this is the OGC API coverages is the next generation of web coverage service. So here you can see hooking up a given data set. In this case, this is a GRIB2 data set. And then we can see some coverage JSON output of the some air temperature data here for this GRIB2 file. In pygeoapi, we also support the OGC EDR, or Environmental Data Retrieval specification, which provides a higher level API for users to interact with environmental data, whether it's multi-dimensional data or whether it's, let's say, a network of monitoring stations that you may have that are measuring certain things. EDR provides the API to query a given collection with some really easy API machinery. So here's an example of getting a coverage JSON from some sea surface temperature using some well-known text in the API URL to be able to get exactly the value of a given pixel at a certain point. You can also combine this with adding a temporal filter, so getting the value at a certain point and at a certain time as well. So that's the idea of querying and slicing through multidimensional data through EDR. Here's an example of the same lakes that we saw in the OGC API features example, but published as OGC API tiles. So this is the idea of providing the Mapbox vector tile format, which is very efficient and lends itself to performance and caching available through pygeoapi here. OGC API records, I mentioned metadata before. So you can after publishing your metadata to OGC API records in pygeoapi, any tool that can connect to that OGC API record service can be able to do spatial queries or temporal queries or free text queries, so Q equals style queries to pygeoapi, and discover a given metadata record. So here's an example of using pygeoapi connecting to the OGC API record service that it supports through the QGIS tool. QGIS supports a number of the OGC API standards, such as OGC API features, OGC API records, and so on. We mentioned OGC API processes previously, so here you can see an example of a definition of a very generic hello world process in pygeoapi, where you see a description of the process and some of the inputs that are required in the process and what some of the outputs might look like. Again, you can run OGC API processes in pygeoapi as asynchronous processes or synchronous processes. So those are the different execution modes that you're able to configure if you so choose. We also support Stack, the Spatial Temporal Asset Catalog. And the way this is implemented in pygeoapi is that you could implement a Stack catalog by way of pointing to a directory tree of let's say GIS files, and pygeoapi will basically crawl that tree and be able to give the user a stack catalog, a browsable stack catalog on disk. We're also planning to support not only crawling a directory tree on disk, but also on cloud, let's say S3 or Azure Blob Storage for that matter. I mentioned the robust plugin framework in pygeoapi as an example of providing extensibility. We also have HTML templating available in pygeoapi. So here's an example of, in this case, GeoConnects US, implementing pygeoapi with a specific HTML look and feel. So this is a pygeoapi implementation, which is not using the default look and feel of pygeoapi, which is very rudimentary in comparison. pygeoapi allows you to create your own HTML templates, whether you have organizational needs or other requirements for look and feel and accessibility for that matter. Here's some good work by the GeoConnects folks to provide their own UI around on top of pygeoapi. And you can develop this totally outside pygeoapi, and you basically have the pygeoapi configuration pointing to a set of HTML templates that can be used and managed and updated accordingly as you deploy your services with these custom HTML templates. So I've given you an overview of the project and all the standards that it supports and some examples of those standards in action through the last section. I'll give you a bit of an update now on some of the things that we've been working on lately in the project. So as I mentioned, pygeoapi started in 2018, and it's been growing constantly. There's been a number of new developers and new community members. Here I'll provide some update on some of the latest developments in the project. In August of 2022, we officially became an OSGeo project. So this was great news. This allows us to put the OSGeo stamp of approval on the project, and by doing that, pygeoapi shows that it's gone through the process of being of providing a rigorous open source process, as well as being in good standing with other with some impressive projects such as GDAL, MapServer, GeoServer, and so on. So this happened around the time of the FOSS4G 2022 event in Florence, and we were happy to announce that we became an official OSGeo project at that actual event. We have new committers in the project. So Joanna Simos, who's with OGC, has joined the project. She's a developer relations at OGC, longtime contributor to not only pygeoapi but many free and open source geospatial projects. She's vice president of the OSGeo Portugal local chapter, and she's made some valuable contributions to pygeoapi in terms of mentoring, in terms of providing outreach, and in terms of providing features and fixes to the code and the implementation with regards to a number of different specifications. So welcome to Joanna. Obviously, we're glad to have her in the project, and she provides some strong capabilities with regards to development and so on. We also added Ben Webb from the Lincoln Institute of Land Policy Center for Geospatial Solutions. Ben is in the U.S., and he's concentrated on a number of activities in relation to the U.S. Internet of Water, and he's also implemented a number of different pygeoapi provider plugins that are required or have been funded through the Lincoln Institute and the U.S. Internet of Water, for that matter. So welcome, Ben, another valuable addition of a very talented developer to the project. OGC API Sprint participation. pygeoapi has made it a priority to try to participate in a number of different OGC API code sprints. So the OGC API code sprints, or the hackathons that I've mentioned previously, are really valuable ways for not only OGC API specification developers, but also developers of software to be able to interact and do interoperability testing and experimentation to build out more OGC API support in software, as well as maybe iron out some issues that could result in improvements in the actual OGC API specifications themselves. So these are really great events. There is a joint sprint that's happened on a yearly basis since 2021, which is a joint sprint between the OGC, OSGeo, and the Apache Software Foundation. We are gearing to have another joint sprint in the first quarter, or March or April of 2023. So for those who are interested in joining these code sprints, whether it's the joint code sprint, which is should be in Q1 of 2023, so keep an eye out for that for more information, or whether you'd like to basically join another OGC API code sprint. They're free and open for people to participate, and you're encouraged to follow the OGC with regards to planning and communication of those code sprints. So having said that, the pygeoapi development team typically tries to be at these code sprints as much as possible, both to collaborate with other software implementations as well as to be able to improve the OGC API specifications, but also to implement features and add new features with regards to the OGC APIs. Other recent developments, there's been some work on OGC API routes. So Skymantics has done some great work with regards to implementing the OGC API route specification. There are some outstanding work or clarifications that are required within the specification itself, but we are really close. And this has been demoed in a number of OGC code sprints in the past. It's a great implementation that uses PG routing as a default. So look for this to be in the pygeoapi core code base in the near future, for those of you that have requirements or interest in routing. At the OGC Metadata Code Sprint in September of 2022, we implemented OGC API transactions. So, as I mentioned before, pygeoapi, for the most part, leaves your data alone, and it sort of has a read-only look or view insight into your data. However, we added support for transactions in the fall of 2022 at the OGC Metadata Code Sprint. This provides create, update, delete. So for update, it would be either a full update or a partial update, but basically we've implemented full transactional capability in pygeoapi, with the focus being on records and features. So this means adding a new metadata record, or adding a new feature to a collection, or updating a certain property of a record or feature, or deleting it itself. And here we can see in a screenshot how this looks in the Swagger interface with regards to that support. So this is valuable for a number of different use cases where we would like to have data editing as part of the API. I should mention that as part of the OGC API transaction support, we do not, the OGC APIs themselves do not necessarily support or provide guidance on authentication or authorization or any access control streams, access control approaches. So this is left up to the server to implement, and we've taken the same approach in pygeoapi. So in pygeoapi, we don't have strong opinions on how to do access control. We leave that to the implementer, whether they wanted to do HTTP basic auth, or whether they want to do some sort of API token or key, or some other kind of access control mechanism. That's left to the implementation. pygeoapi assumes that once the user is able to access that given data set, and if the data set is editable, so you can set that in pygeoapi itself. By default, all data sets are defined as read-only, but if you choose to make a data set editable, then a user will be able to edit that data using the OGC API transaction design patterns. In late November of 2022, at the OGC Web Mapping Code Sprint, we implemented OGC API Maps support. So the idea here is OGC API Maps, which is designed to supersede the Web Map Service specification. This was implemented in pygeoapi. We implemented two ways to connect your data and expose it through OGC API Maps. One is through the map server, the UMN map server tool, providing support through its map script Python capability, and the other one is basically a WMS facade, which basically means you can configure an OGC API Maps capability in pygeoapi by connecting to an existing WMS, and a user will provide the OGC API Maps request, and pygeoapi will translate that into a WMS request and provide the map as expected by the user. So it's really a nice wrapper or a bridge for those wanting to provide easy OGC API Maps services on top of their existing WMSs. And this was implemented again at the November 2022 code sprint for web mapping by OGC. We've also implemented in summer of 2022 at the OSGeo Code Sprint after the Florence Phosphor-G event, support for Django as a web framework. So I mentioned that Flask and Starlet are web frameworks that are supported by pygeoapi. We've also added support for Django. So this gets really powerful when you want to add geospatial OGC API capability to your Django app. So pygeoapi makes this really easy with pointing to a ready-to-use Django app folder with predefined routes and predefined views, which basically binds all the Django machinery into the pygeoapi core API, for that matter. Hierarchical collections. We also implemented the ability to have collections as hierarchies, so you can have an infinite number of levels to a collection by delimiting them with slashes. So here's a simple example of how you can do hierarchical collections in pygeoapi, and there's a link there to the documentation to find out a bit more about it if that's of interest. That was implemented in 2022 as well. More new features. We moved on our default HTML look and feel. We migrated from using mini CSS to Bootstrap itself. We also implemented hidden resource publication. So this might be where a situation where you would like to make a resource available through pygeoapi, but not necessarily publicize it. You may want to have some experimental data or experimental collection for a given point in time. So through some easy switches in the configuration, you're able to do this by providing hidden resources, if you will. We also added a number of different new provider plugins. So Esri provider plugins feature provider plugins for Esri and Socrata. So Ben Webb implemented those, as well as Stack-based HateOAS provider plugins. We implemented anti-Meridian support, as well as gzip support. So I've gone through some recent updates in the project. Now I'll give a bit of an overview on some of the options on how to install pygeoapi. There are a number of different deployment options. We're on the Python package index, so you can install via pip3 or what you see on pygeoapi.io, the website, with a quick install, the 5-minute install. We're also available and up-to-date on Ubuntu GIS, which powers OSGeo Live. We have our own Docker images, which are made available through Docker Hub. And we also have the same capabilities to install through Conda, BSD, and so on. So a number of different ways to install and deploy pygeoapi depending on what your deployment design or pattern is, for that matter. Again, a very popular installation method of pygeoapi is using Docker. So we have our Docker images on Docker Hub, and this gives developers and DevOps people full flexibility to install and configure pygeoapi through a Docker or a Docker Compose approach for their given application. There's a very simple Docker pull and Docker run workflow, which uses the default latest image, which is based on master, as well as you can see some port binding there. So at the end, pygeoapi on Docker by default runs on port 80, but here we can see somebody deploying pygeoapi mapping to port 5000 instead, so as not to collide with other ports maybe on their system, and you can see some sample requests down below on how to interact with that resulting Docker deployment. Again, you can customize your Docker setup with custom Docker volume mapping. You can run things with Docker Compose and maybe override things. You can do subpaths with pygeoapi, for example, by overriding the script name environment variable. In the link in this presentation, the examples, there's a number of different examples we have in the code base on what you can do with pygeoapi and Docker. And having the Docker support gives you the capability to scale pygeoapi accordingly. So if you're interested in providing high availability of pygeoapi, it does lend itself to that kind of deployment architecture, as you can see in this diagram. Now I'll walk through some examples of production instances of pygeoapi. So in addition to pygeoapi rapidly supporting all the OGC API standards and participating in a lot of innovation and research and development, it's also used in production by a number of different major organizations, which really lends itself to showing how mature and stable the project is, given its use in a number of big API projects across the world. In Canada, at the Meteorological Service of Canada, we run the MSC GeoMap platform, which is our OGC Web Services platform, Canadian weather, climate, water data. It includes real-time weather data, as well as numerical weather prediction data, as well as archive data. So either water levels, hydrometric data, and climate archives as well. So there's a real-time and an archive component to our MSC GeoMap platform, and pygeoapi powers a big part of that platform in making MSC data available through the OGC APIs. And here you can see some of the websites that are deployed by MSC with regards to pygeoapi. api.weather.gc.ca is our core capability, and you can also see that used in the Canadian Centre for Climate Services data portal, as well as climatedata.ca. Here's a simple view of MSC GeoMap using pygeoapi using a custom look and feel. So you can see the landing page there. So I mentioned before that you're able to do HTML templates with pygeoapi, and here's an example of how we've done this in the Meteorological Service of Canada. Here's a simple view of some climate stations in pygeoapi with a custom look and feel again. And here you can see at the bottom we've extended the default template, and we've provided being able to filter by a given property. So a lot of extensibility done to this HTML look and feel. WIS2 in a box. So in the United Nations World Meteorological Organization, there is an activity that's going on that's called WMO Information System 2.0, or WIS2 as we call it. This is designed to basically provide the next generation of weather, climate, water data exchange for the World Meteorological Organization and WMO members for that matter. It's very heavily rooted in event-driven data exchange, and a big part of that is providing this WIS2 in a box reference implementation, which is being designed to help WMO members publish their data to the WIS2 network, as well as consume data from the WIS2 network. WIS2 in a box itself offers an API component to be able to make data available, published to WIS2 in a box as OGC APIs. That API component is powered by pygeoapi itself. And here we can see a simple view of some stations in WIS2 in a box that are in Malawi, and that is a pygeoapi OGC API feature service, which is powering the points on the map. And here we can see that same feature service is also powering time series of various surface weather observations, for example. The USGeoPlatform.gov was released earlier in 2022, or at least that's when it was announced. It provides a central point of access to federal geospatial metadata services and data, really rooted in the FAIR principles. A number of FOSS4G components are part of US platform, geoplatform.gov, and there's over 100 data sets at this point. So you can see the website in action at geoapi.geoplatform.gov. And there's a small screenshot of the application with a custom HTML look and feel. We also see pygeoapi being deployed in Europe as part of the Emotional Cities project, which is basically designed to mapping cities through the senses of those who make them, and lends itself to urban living and mental health and well-being. BGS, The British Geological Survey has deployed an OGC API server that is primarily focused on OGC API features. I should probably give a shout out to BGS for doing some really great work on extending pygeoapi's Postgres support. So they've done some great work in supporting the CQL or Common Query Language through Postgres for that matter, and they've made that available through their OGC API server, which is powered by pygeoapi. The GeoE3, or the Geo platform, is providing a geospatially enabled ecosystem for Europe, and it's a data integration platform. So we can see pygeoapi being deployed as part of that project as well. Another example of a custom HTML look and feel. In the US, the GeoConnects project, I had a couple of examples of geoconnects.us previously, is really focused on knowledge graph linking of hydrologic features in the US, and it's really rooted in the spatial data on the web best practice by W3C, and you can see pygeoapi in action at geoconnects.us. River Runner. This is a really cool application. This is based on OGC API features and OGC API processes. So the idea here is being able to click a given point on a river and seeing the entire stream. That's done in real time through OGC API processes on the River Runner website. So there's a great example of the River Runner in action, and that's OGC API processes and pygeoapi for that matter being used under the hood to draw out the path. Roadmap. We've given you some background information as well as what pygeoapi is currently up to and recent implementations and who else is using it out there. What are we looking to do in the future for the project? Obviously, we want to continue to improve our support of OGC APIs. This means not only improving the way we implement those OGC APIs, but also moving along with the specifications. Some of the OGC API specifications are still working towards a 1.0, and we follow those OGC API implementations so that we can implement those 1.0 when they get there in pygeoapi itself. Obviously, there's no shortage in work on connecting more kinds of data and data workflows to pygeoapi. So we're seeing a lot of different people working with data providers and writing their own plugins. Some of these plugins will end up in pygeoapi core. Some of these plugins will live outside the core, which is totally fine. That is the design of pygeoapi, and that is the core principle in being able to support this core and extension framework. Given all the OGC API standards that we support, and given the rapid development that's happened in the last couple of years, we do want to undertake some time to deal with some technical debt and do some small refactoring and pre 1.0 adjustments. So right now, pygeoapi is at 0.13 as of December 2022. For us to get to a 1.0, we do want to make some adjustments and refactoring to make sure that we set the project off on a good way for 1.0 and beyond. GeoNode integration. So GeoNode is now has a new V2 REST API, which is merged into master, and there's a number of discussions that are going on in the GeoNode community that have happened in the past around possibly integrating pygeoapi deeper into GeoNode with regards to the data the data API backend. And this is loosely related to some of the work that's been going on in the Django implementation for pygeoapi being able to tie to a GeoNode instance. So stay tuned for that one, and hopefully we'll see some deeper integration as time goes on. Support. So we have a wide-ranging array of community members, from users, testers, developers, folks working on documentation, and so on. Where do you get support for pygeoapi if you'd like some core and custom development for that matter. So we do have a service providers list on the pygeoapi website. So if you're looking for training or support for setup, installation, deployment, if you'd like some custom development from a service provider or anything for that matter from pygeoapi to help your pygeoapi story, then we do have a list of service providers that's available at the link below. Having said that, I will leave this list of links here for a minute, where we have a number of different links on how you can interact more with the project. So whether you're looking for documentation, or if you wanted to look at our core demo, which is at demo.pygeoapi.io, this is again, our core demonstration server. So at any point in time, you can see what pygeoapi is all about by looking at our default demo. All the source code is on GitHub. All of our issue tracker and releases are also done on GitHub. We have a Docker capability, as mentioned previously. Developers on pygeoapi are typically in the Gitter channel that we have there. We also have a mailing list for any discussions, as well as release announcements, and we have our own Twitter channel as well. And the pygeoapi community is ready to help. Either if it's a developer or a user or other type of community member in pygeoapi, it's a welcoming community, and we welcome more users and testers as well as developers to be able to improve the project over time. With that, I'd like to thank you for your time. I hope this overview of where pygeoapi come from, some of the core features of the project, and some of our vision for the future. I hope this has been valuable in terms of an overview of pygeoapi, and I wish you luck. And if you're interested any further, feel free to contact us at some of the links that we provided below earlier. Thank you.